Okay. On reverse engineering. Oh, that's yours, right? No? Okay. Whatever. Anyways, it should be interesting. But we'll get straight into it. So I didn't put like an intro slide, but I'll be going over just kind of the basics of RF hacking and just how RF stuff works in general. So if you have no background on how radio stuff works, then hopefully this will be the baseline to get you from the weird physics hardware side to bits and bytes that you can start decoding that hopefully you're more familiar with, or at least are a little bit more accessible to you. So to start out with something you probably already know, there's a bunch of different frequencies that stuff can be operating on. Typically you'll see lower frequencies will be longer range, so you have like AM radio, weather radio, any kind of broadcast stuff is going to be on a lower frequency. And higher frequencies, you have more oscillations in a certain amount of time, so that means you can put more data through. So a great example of this is if you've used 2.4G Wi-Fi and 5.8 gigahertz Wi-Fi. The 5.8 gigahertz is a lot faster, but it's not going to reach as far. So that's just the general trade-off with different frequency stuff. And you'll see on the next slide, the RF spectrums divide up into a whole bunch of stuff. Antennas are, I think I have this on the next slide actually. Do I? Where'd my other slide go? Okay, I put it in a weird order. All right, yeah, so antennas are tuned to a certain wavelength. The wavelength is, if you remember from physics, that's the lambda, and then it's velocity over the frequency. The velocity in this case is the speed of light, which is a big number, but it comes out to about 3 to the power of like 10 to the 8 or something. But for our purposes, we don't really care about the exact number. You can use a really nice conversion. If you want to find the wavelength of something, you just get the frequency in megahertz and then divide 300 by that, and that'll get you roughly what you want. So I thought about zooming in on this, but just to give you an idea of like how much stuff there is going on around us, this is the FCC allocation for all the different frequencies. So in here you'll see stuff like the different mobile carriers. They have different stuff going on. There's like aircraft signals, naval signals, all kinds of emergency broadcasts, and then some even more crazy stuff going on. So just there's a lot going on. If you see a random signal, it could be a ton of different things, but all of these little sections are well regulated. So in general, if you see a signal within some section, you can kind of get a rough idea of what it's for. So yeah, there's the same calculation I had, but antennas you'll usually see they come in half wave or quarter wave. So let's say I have a 2 meter long radio wave. So that literally comes out to, that means the oscillation is on 2 meters. So if I wanted to effectively transmit all that, I have to build a half length or half wavelength antenna, which is 1 meter long. And that's kind of inconvenient. So if you want to squeeze it into an even smaller package, you could do half a meter, and that would be a quarter wave antenna. The downside to that is that the smaller antenna sizes are just generally not going to be as efficient. But for things like phones and stuff, you can't really fit the full length antenna in there. So you'll see that pretty often. Antenna design is the voodoo magic of RF. I understand it, and even if you take like some classes on it, it's still going to be very complicated. So, but in general, it doesn't really matter. You can, an antenna is tuned for one wavelength, but it'll accept other wavelengths that are nearby pretty well. So if you're just close enough, for most purposes, it's going to be good enough, because we're hacking stuff. Usually we're trying to hack something in front of us, not something that is 10 miles away. So we don't have to worry about that. So here's a nice animation. Why do I have like 4 slides on this? Here's a nice animation of how it works. It explains nothing to me, honestly, but like I said, voodoo magic doesn't matter. There are different kinds of antenna designs. The most common one you'll see is a dipole antenna, so just a straight line. You'll also hear these called rubber duck antennas for some reason. But basically this gives off that signal path like you see on the top there, which is just a radial signal, and then there's 2 null points, which is just the top and the bottom of the antenna. So if I want to transmit from one dipole antenna to another dipole antenna, it's best to have them parallel with each other. And sometimes you'll see, like if you've ever set up, or you've seen like a TV receiver box, they have the 2 antennas on the top, they'll be 90 degrees offset. That's because the 2 nulls will cancel each other out, so you won't have any dead zones, and hopefully you'll get all the channels you're looking for. Antenna gain is something you'll see very often. That's basically just how intense is this pattern. So if I have a very high gain dipole, it's going to be very sensitive on the sides, and anything on the top or bottom, it's not going to receive well. Generally, you won't see that with dipoles, because if someone wants to get a signal a very long way, they'll use something like a helical antenna or a Yagi antenna. These are just different designs named after stuff. But you'll see like that bottom design, or that bottom pattern is very directional. So whatever you point it at, that's where you're going to get the signal from, and nowhere else. So with RF, there's a bunch of different types of what's called modulation. It's like, how do you turn this wave into data? If it's just a single wave that's constant, then it's not going to be very useful to you. You're just going to get the frequency and nothing else. So you have to make changes to this wave. That's called the carrier wave. So you have your frequency, let's say like 1 gigahertz. You're going to have an oscillation that's a sine wave going at that frequency. And in order to make changes to that, you have to do some of the stuff we'll see on the next slide. But in general, there's you can see there's a bunch of different modulation types. The main ones you'll see in radio are with these analog carriers, and you're probably familiar with AM and FM, at least by name. But generally the trade-off is you'll have a higher data rate and lower signal integrity. So with if you have something that is cramming a bunch of bits into a very small space, you're not going to have very good resilience against random solar radiation or other stuff like that, or signals bouncing off walls and coming back and interfering with itself. So these are a lot of the stuff that generally you don't have to worry about unless you're designing a radio signal, but they are good things to keep in mind. So we'll get into some of the modulation types. Very nice animations provided by Wikipedia. There are 3 main types of analog modulation. There's AM amplitude modulation, where when it goes up when the signal goes up, and it goes down when the signal goes down, but it's just oscillating at a much higher frequency. That would be your carrier frequency. Then you have frequency modulation, where the carrier frequency is just kind of the center, and then when you have the signal go up, it oscillates quicker, and then when you have the signal go down, it oscillates slower. And so you're able to, this is more resilient to stuff like distance. So if you have an AM signal, as you drive away from that signal, you're going to lose amplitude, and so then the signal is going to be weaker. You could misread a bit or something like that. So that's why you'll generally see FM broadcasts sound a lot better, at least in the car radio sends. And then there's one more, which is phase modulation. This one isn't as common for analog signals, but basically you have two different signals. So this orange one here I'll show it on the monitor. So this orange one here is your carrier frequency, and this blue one is the data you're trying to transmit. And so this changes, this modulates this here with some nice trigonometry. So you end up with this signal on the output. And then what you'll probably see more often if you're trying to hack stuff is digital modulation. Digital signals are nice because they either are a 1 or a 0, and it's if there's interference or something, you don't lose data completely. So there's 4 main types in this case. There's FSK, which is frequency shift keying. This is just like the FM, but in a digital sense. So it either is faster when it's a 1 or slower when it's 0. That's all you have to worry about. Again, same thing with ASK. That's just like AM, but in a digital sense. And then one more time, you have the phase shift keying. This works in a similar manner to the analog equivalent, but you're just moving back and forth between 2 different phases. So, you have this nice smooth sine wave. It goes up and down. Whenever you have a 1, it changes 90 degrees usually out of phase. And then when you go back to a 0, it changes. So just on every change, it changes the state. And there are some variations of this just for all kinds of random reasons. But there's also a 4th kind, which is quadrature amplitude modulation. This is a little bit more complex. If you're interested in this, you're going to have to learn a lot of math. But it's basically 2 AM signals combined together. So you're able to get like 2 bits of data out of a single carrier or whatever. And I believe this is, QAM is used for Wi-Fi. So if you're doing any kind of low-level Wi-Fi attacks, you're going to see that. Bluetooth uses frequency shift keying, but it uses a slight variation on it called Gaussian frequency shift keying. That just allows it to be a little bit lower power. You'll see with all 4 of these are the only ones you'll really see. But there are like hundreds of different variations of these. So for different reasons, people try and engineer the signal to be perfect for what they want. So the cool thing about radio is we have this nice regulatory body, which is sometimes against us, but in most cases, the FCC is very helpful when you're hacking stuff, because anything that has a radio in it that is meant for the general public to use has to be validated by the FCC to make sure it's not interfering with emergency signals or anything like that. So if you've ever gone into your phone's like details, where it has like the build number and software version and all that, you'll see the little FCC ID. Or if you looked at something wireless, let's see if this radio pack has it. Beautiful. You can't read it, but this lavalier mic has an FCC ID on it. And so what I could do is look this up. If I don't have physical access to this because I don't own a lavalier mic, I can just take a picture and then look it up on fccid.io. That's someone's made a website because the FCC website sucks. But you can look it up and find usually pictures of the inside, and that'll give you some general idea of like how the electronics are functioning. You can see what kind of frequencies it's outputting on, what the signal strength is. So lots of cool stuff. Like if you ever have one of those restaurant pagers, you can't even buy those like anywhere. So if you want to hack it, you'd either have to steal one or look it up, but luckily you don't have to. So this is an example. I think this is AirPods. There is a lot of documents for this because I guess Apple is a very big company. But all of these reports have tons of data, which you'll have to probably sift through if you're trying to hack stuff, but better to have it and not need it than need it and not have it. Yeah, so lots of cool stuff there. In addition to that, there's also radioreference.com that kind of helps you, that huge spectrum graph I showed earlier, that helps you break it down and see what's relevant in your area, because different states and cities will use different frequencies for stuff. So if you want to listen to police radio, you can see what does the city of Richardson have clearance for, and radioreference.com will have that, so you can tune in and listen, assuming it's not encrypted, which a lot of them aren't. So the cool part about this talk is SDR, which is software defined radio. Basically, instead of having something like this where you have to tune it to a specific frequency, you just take everything. You say, just take a bunch of samples of stuff. So it's like, your antenna is giving an analog to digital converter a signal, a different voltage, and you just take a bunch of samples of that. You say, what voltage is this at this time? And so in that case, your x-axis is a bit depth on your analog to digital converter, so it could be like an 8-bit value from 0 volts to 5 volts or whatever, or sometimes you'll see 12-bit for radio stuff, but that's your bit depth. And then you have the x-axis in this case is your sample rate, so how many samples are you taking per second. If you want to decode a 5 gigahertz signal, then you're going to have to be sampling faster than 5 gigahertz, because you need to have 5 or 6 points per each wave. So when you get to those really high frequencies, sometimes you'll see these radios will have filters and what's called an FPGA built in. So it can do some of the basic modulation or some of the basic demodulation on the device, and you're not having to fill up your RAM with hundreds of gigabytes of points, because that can happen, especially when you think 5 gigahertz signal. My CPU runs at this one probably runs at 2.4 gigahertz. Not very fast. It's not going to work. So you won't be able to do that demodulation live. These are just 3 of, I think, the most common software-defined radios. This RTL SDR is based off of a TV tuner, and they're like $24 on eBay or on Amazon or eBay or whatever. It does receive only, and not a huge range, but it'll cover a lot of the spectrum, enough for you to play around with. A step up from that, I think the most well-supported one is the HackRF. That can do anything from 10 megahertz to 6 gigahertz, so that covers most devices you'd see. And it can do transmit, but not at the same time as it's receiving. And then there's just another one here, the Pluto. So once you have a SDR, you can get something called a waterfall plot. What this is basically the spectrum mapped out. We can see from 102 or 106 megahertz to 107.2 megahertz, and we can see all the signals going on in here. So this looks like an analog signal here. This is probably a digital signal, another analog signal, and so you're able to kind of visualize what's going on the spectrum. The color is just how strong the signal is. And then obviously the x-axis here is the frequency of the signal, and it just scrolls through over time. And we'll play around with that later. But this is a great way to kind of visualize it. If you're trying to find let's say you have a garage door opener and you want to see what signal it's transmitting on, you just hit the button. You see, oh look, there's a line that popped up there. I can zoom in on that and start trying to decode it. So that was generated with what's called GNU Radio, which is a piece of software that it's open source. I believe it's Linux only, but you can run on a Raspberry Pi or whatever. And it's a nice like graphical way to do digital signal processing. So you have all these samples and stuff. They're not very useful on their own. You want to demodulate it, but there's hundreds of different protocols for that. So you can kind of take the basic building blocks in GNU Radio and build it out. So in this case, it's taking an audio source, so literally plugged into your audio jack in your computer, your line-in jack or microphone jack or whatever. And I believe this is an AM decoder or something, but it doesn't matter. You can look into it more yourself. But it's very user-friendly, and then this generates Python code. So if you want to write your own block that does something very specific, you can do that there. But you can get like 90% of the stuff out of the way with these pre-made blocks. So just going over a few different types of attacks. The most common one, or the most, the one you've probably heard of, is jamming. Jamming isn't really super interesting in my opinion. It's just denial of service. So if you can see on this waterfall plot, someone's radio is just sweeping through the spectrum and sending out a bunch of garbage. So anything on that part of the spectrum is not very useful. But it is a very quick way to get in trouble with the FCC. So don't play around with that. If you are interested in getting into some of this stuff, I'd recommend getting a ham radio license. That's it'll teach you. You're required to learn a lot of the laws and stuff. But then you're also, once you have the license, you can transmit on a whole lot more frequencies than you're allowed to as just a normal person. So it's fun for playing around and learning, and that whole system is there just for education. So it's pretty good. Then you'll see, then there's another really common attack is a replay attack. So that's where you basically record a signal and then play it back. If the garage door opener, you press the button and it opens the garage, well, what happens if I just do what that thing transmitted? Will it open the garage again? A lot of times it will, if it's something very simple like that. Or even if it's something more complex, like, if I have an IoT device that's working over Wi-Fi and it sends the same packet every time, then, if I record it, I don't even need to know what's in the packet. I can just replay the packet, assuming there's nothing fancy going on there. So, cool example of this is there's a Black Hat talk called Siren Jack, which kind of goes more into it. They didn't do the attack, but in 2017, the Dallas emergency alarms, if you've ever heard like the storm alarms go off or tornado warning or whatever like that, they were able to record basically the signal that's sent out for the testing at like noon the first something of each month. And then they spotted a pattern. So like when it was transmitted, once they were able to like decode the signal, which was using what's called DTMF, which is basically when you if you've ever dialed a phone and you hear the boops and you played a song, because they're all different tones, that's just encoding 1 through or 0 through 9 in audio. So they're able to decode that and decode the packets and figure out what's going on there. And it just changed 2 bytes based on the time of day. So literally all that they had to do to set off the alarm was take the last message that they saw transmitted and then change those 2 bytes to correspond with the time that it was, and then send that out, and it was able to trigger, hundreds of alarms because it wasn't properly secured. So, yeah, it's a very good talk. I recommend watching it. Kind of variation on this, which I don't know. I'm sure there's probably a more official term for this. Was popularized by something called roll jam, which was basically hacking cars or unlocking cars with a combination of jamming and a replay attack. So cars work with something that's called a rolling code, which is basically every time you press the button, you get it sends out a different code, and the code only works once. But the code isn't time sensitive at all. So if I know what the next code is, I can play it from anywhere and at any time, and then it'll unlock the car. So in this case, what happened was whenever you basically planted a device on the vehicle or near the vehicle, and whenever you hit the button to unlock your car, it would immediately start jamming on the frequency that the car is trying to receive, or I believe it's jamming near the frequency that the car would receive. And these systems are built with so much tolerance that if there's a signal being jammed near what it's trying to receive, then it's not able to receive anything. So in turn, the car doesn't unlock based on that code, but you're still able to listen to the original signal and save it for yourself. So in that case, you hit the button, it doesn't unlock the car. So what do? You hit the button again, and then it unlocks the car. All right, you're good. But what's actually happened is you hit the button the first time, the device saved the original code, and then when you hit the button the second time, it saved the new code and replayed the old code. So now it has a code that is one in the future, and you've unlocked your car, you're fine, you don't think about it. But the next time when you walk away, the attacker now has a code for your key that your key is already used, but you aren't aware, but your car doesn't know has been used. Yeah. I'm just gonna add. Can ask questions here. So, anything can be a radio. Like I said, there's a lot of really complex stuff going on with radio, but you don't really need to worry about it because, all a radio is a bit of magnetic radiation changing at a certain frequency. So literally, you can see in this picture here, this is a Raspberry Pi with a jumper header or a jumper wire attached to the digital to analog converter. So so there's just some software going on that's saying, move change this pin to output a signal that looks like this wave, and that jumper wire works as an antenna. And so this is a functional radio. This can work to transmit FM radio to your car or phone or whatever. Okay. So some other interesting examples of this is Tempest is like an NSA. I guess it's a category for a certain, like some certain tools, but they're doing what's called side channel attacks, which is basically stuff you wouldn't think of. And back in like the 80s, the CRT monitors, because of how they work, they give off a bunch of electrical interference, and from another room you're able to record that and maybe reconstruct what's going on someone's screen. And there's a bunch of other stuff that's more modern, similar to that, like AirFi, AirHopper. This is just like one guy who just comes up with, it's a research team, but mainly it's just one guy who comes up with different ways to get out of air gap networks. So if there's no network connection or no anything, it's like, well, how do I get data out of that server? Well, what you can do is, if you've taken over the server, you can change the RAM, like change bits in the RAM really quickly, and that'll give off interference. So if you just change it in the pattern of a signal, then you can all of a sudden read the signal if you have good enough receivers. And AirHopper is a similar thing, but it's using GPU emissions. So again, it's like if I load up the GPU to do a bunch of processing at this moment, all of a sudden there's more interference being given off, and then I stop doing a bunch of processing, there's less interference. That's my 1 and 0. I can exfiltrate data with that. So lots of really interesting stuff in that case. So now, if there's no questions, then we can go ahead and play around with something called WebSDR. And this is basically just a website where people with their software-defined radios can host it publicly. So you can play around with other people's radios if you don't want to buy one, or you're just curious what, Puerto Rico sounds like. I think we scroll down. There's a map somewhere. Yeah. All right. Where do y'all want to listen to? South Africa. All right. Hopefully, we'll see. Hopefully this works. Okay. All right, here's our waterfall. And there's not a lot going on in South Africa. So here's a signal. You can punch in on it. This is a really high frequency. Okay, I don't know what that is, but you can start. I mean, it's clearly some kind of digital signal. But if you wanted to record this, you can just save it as an audio file, like a WAV file, and then plug that into GNU Radio and start playing with demodulation. So, see what, if I looked at the waveform, what does this look like? And you can start building that out, or maybe just based on what frequency it's at, you can figure out what's going on. Let's go to another one. The US has pretty active or Russia. How active do we think radio is in Russia? Blocked, that's great. Malware. Fantastic. Probably just based on the .ru. I mean, these are just self-hosted web pages, so. I guess, yeah. All right, here's local Dallas. Oh, that sounds like people. Nope. Okay, we'll try something else. It's in there somewhere. So yeah, you can play around with that stuff. There's lots of public signals. You can listen to. I believe I have police radio, air traffic on this, other stuff. But if you don't have a radio, you can just play around with this, and literally all you do is just zoom in on the signal. If we go down in the spectrum, we can probably see some like Morse code or something. Yeah, so this is just I think it should have on the listing. What was this called? W2DB. And so these little acronyms you see, those are people's call signs. So if you get a ham radio permit, then you'll get a call sign, and that's what you have to. If you're about to broadcast, then you have to say this is my call sign, and that way if there's some kind of interference or something going on, they can track it down, tell you don't do that. Or if you don't broadcast your ID, then what they can do is just track down the signal, because it'll get stronger wherever you are. So don't mess around with radio stuff. So this is a RTL SDR. So again, this is just a $24 radio, and it's hooked up to a Raspberry Pi and just in someone's probably attic or something. Oh, there we go. I think so. Yeah. I believe so. Any Morse code enthusiasts? Well, if you wanted to, there's GNU Radio blocks to decode this stuff, so you wouldn't have to learn it. Aren't computers great? Anyways. Yeah. And again, like just this, there's just an audio recording button, and you can do it's like just recording everything in this spectrum that I'm zoomed in on. And you'll see, like when I zoom out, it's not actually recording anything outside of this. So that's just a limitation with software-defined radios, is you can only get so much bandwidth through. So when I'm zoomed all the way out, I'm just getting very rough estimates of where stuff is. But if I actually want to decode the signal, I'll want to zoom in and get a much more defined version of it. So let's see, do we have any questions? Where'd my little presenter thing go? I guess I exited it. Will anyone have questions here? If not, that's all I have for today. Thanks for coming. We have food, so.